Okay, so this was, I think this was question number 14. So this would be a 1 mark question. Okay, so this was a 1 mark question, and it was a very simple question as well. So any of you want to try this question now? Any ideas? Let's have a discussion, kind of. Anyone? Mudireddy, will you want to try?
Yeah, ma'am.
So
So,
we can discuss it here
option B,
only.
like
Huh.
when we give EN 0, then both the MOSFETs will be off.
When En is 0, okay, then what will be the option? What will be the output?
High impedance state.
Okay. So what is the option you want to go with?
Option B.
Okay. So anyone else? Chandrasekhar or Hari Prasad? So the way you approach the question is that you can write okay, I'm writing but it is not coming up. Do you guys can you guys see anything like enables one output? So enable D and F, right? So first thing is when enable is 0 and the input is NAND gate, right? So what is the table of truth table of the NAND gate? Truth table of NAND gate is if any one of the input is 0, the output will be 1. That is NAND, right? And what is NOR? NOR is just the opposite case. So if sorry, I have written it wrong. So yeah. So for NOR, what will happen? If any one of the input is 1, then that turns out to be 0. So this is what is NOR, right? So you can see the truth table. This is what NAND and NOR truth table is. So if any one of the input of a NAND gate is 0, that means what? That means the output is always 1. Okay, so the output is 1. And now you see the enable bar is going to NOR gate. So this is 1. And if any one of the input of NOR gate is 1, then the output is always what? If any one of the, I have written wrong truth table. So this is 1, this is all zeros. Yeah, this will be the truth table of NOR. Okay. So if any one of the input is 1, the output is always 0. So now this is basically our inverter. So if you see this part, okay, if you see this part, this is nothing but an inverter, right? So you are basically biasing it through a digital logic. That is what we are doing. We are biasing through a digital logic. Okay. So right now here it is 1, it is 0. So what will be the output? So if this is 0 and this is 1, that means the PMOS is also off and NMOS is also off. That means F is not going to have any output. It is off. So it is not 0. Okay, it is at a high impedance state. Therefore, in the options you see high Z. That means high impedance. Okay, so we have already have this that okay, option will be either B or D because at enable 0 we have F as high impedance. Okay, so now you will see after this next part is when enable is 1. So when enable is 1, then this input is 0 and you see now when NAND gate if one of the input is 1, okay, so then there can be a issue, right? Then there can be a issue. Yeah. So if one of the input is 1, then you have to see what my output will be, right? So then what we will do? So if one of the input is 1, then this one is D and this is D. So the output here is what? D bar, and output here is also D bar. So now in that same inverter, the input is D bar, and since it's an inverter, what will be the output? Output will be D, right? So out of B and D, now the option is B. Correct option is B. Okay, so in this kind of a question, you can actually do silly mistakes might happen, and therefore you may end up taking more time than usual. Okay, otherwise this is a very simple question if you see. But if you can, in exams, when you see this kind of simple questions, it's better to write the truth table. Even if it is memorized in your head, it is better to write it, the truth table, so that silly mistakes don't happen, because that is what we normally do. In GATE exam, this happens that you will get overconfident, and you will do a slight mistake, and the wrong answer is always there in the option, right? And you end up marking the wrong answer is always there, because its job is to to delete those guys who will mark it. Okay, so better write the truth table. That will be my suggestion. Okay. So I hope this question was clear. It was very simple. Okay. So next question. Yeah. So what is this circuit? Okay. So what is Navneet? If I get time, then at last I will take it again. Okay. So you can follow from question 15. Okay. We'll take it up again later. Well. Okay. So yeah. So question number 15, what type of circuit it is? So better again you try to solve and see. Okay. So what I will do is, if you see the circuit like this, it seems complicated. So what we will do, we'll redraw the circuit. Okay. So I'm redrawing the circuit. Nothing, I'm just separating the inputs. Okay. So please follow what I'm doing. Now you would have seen this kind of a circuit, right? In Okay, so it has not yet come because of my internet. Let it come, then we will start. B A, this is B, this is A, B. Don't know what to do. You guys are not able to see the redrawn circuit, right? Yeah, so just let me reconnect and show you guys. Oh, it's not sharing also now. Yeah, okay. So this is how I have redrawn the circuit, okay? So you would have seen this kind of a circuit earlier, right? This looks like a NOR circuit, right? CMOS logic, if you know, this looks like a NOR circuit. Yeah, okay. But is it a NOR circuit? No, because in NOR circuit, what happens? VDD is there, and then you have ground. NMOS is connected to ground, right? This connection is ground usually, right? So, but here there is no ground. Here what is happening? Here you have A and B connected. So if you carefully see the diagram, I have just redrawn it. So these two transistors, the bottom transistors, are working as pass transistors. They are just passing the logic. So what they will do, depending on whether this, and since from symbol you will know, right, that these two are PMOS. From symbol you will know these two are PMOS and these are NMOSs, right? So NMOS is on when gate is 1. Okay, so NMOS on when gate is high, right? And PMOS is on when gate is low. For digital logic, you will remember this. Okay. So now what will happen? That when my NMOS will be on, it will simply pass this value. So if B is 1, then A will come here. Okay, it will simply pass A. Okay. So now what will happen? So again my thing has gone. So I don't know what to do with this. I cannot take class like this. Okay. So what will happen is that you can just write again the truth table. Okay. So A, B, you write all the combinations for 2 bits. Okay. So these are all the possible combinations. Okay. So now if you see, if A is 0 and B is 0, so if both of them are 0, okay, what is happening? If both of them are 0, nothing goes from the NMOS side, right? Nothing passes because both of them are 0, NMOS is off. Okay, so in this case, NMOS is off, right? But the PMOS is on, right? Because A and B are 0, so PMOS is on. And since PMOS is on, F will be equal to VDD. PMOS on. F will be equal to VDD, right? Now, let me take the 1-1 case, right? Or let's say, let's take 0-1 case. So now what is happening? This is A and B. So B and A was here. So yeah, A is 0 and B is 1. Now if B is 1, then what will happen? So now if any one of them is 1, then what will happen? The upper PMOS, one of the PMOS is off. Now if one of the PMOS is off, nothing comes from upside. From up there is no closed path, right? If one of the PMOS is off, there is no closed path, right? And it will be something like this, right? So this is an open circuit, so no current flows. So there will be nothing from up. What we will see? We will see it from down. So now you see, if B is 1, then A passes, right? And this one, A is 0, so this NMOS is off. But because of that NMOS, which is having B as input, A passes. So I am writing A. I'm just writing A for now. F equals to A. Okay. Now in the other case, B will pass because A is 1. So if A is 1, B will pass to F. So I'm writing B, right? And when both of them are 1, what will happen? Output is 1, right? Output is 1 because both of them are 1. A and B both passes, so output is 1. So now my F is 1, A, B, 1. So now what is A in this case? A is 0. Okay, and what is B in this case? B is 0. So output is 1, 0, 0, 1. And what is 1, 0, 0, 1? Which gate? So XNOR gate, right? XNOR gate is a matching identifier. So when both the inputs are equal, XNOR will give you 1. So it identifies matching values. So 1, 0, 0, 1 is XNOR. The answer is B. Okay, this was also a 1 mark question. You see? So you need not just see it and think, oh, whether it is a latch or a SRAM or oh, this is an out of syllabus question. Don't think these things. Just try to solve the question. Okay? Any doubts here? Anything?
Ma'am, last point 1-1.
Oh, so okay. So when A is 1, B is 1, what will happen? When A is 1 and B is 1, the upper two MOSFETs are off, right? PMOS is off. So A is 1, B is 1 means these two NMOSes are on. These are pass transistors. So these are like short circuit. So B will be transferred, and then A will also be transferred, right? So one is transferring, that's it. Okay.
Oh, okay, ma'am. Okay.
Yeah. Okay. So should we go to next question?
Yes.
Okay. So another question. Okay. This was also an interesting past transistor logic question. So you see this 2019 paper IIT Madras made, and IIT Madras has a very strong hold in VLSI. Okay, in both digital VLSI and analog VLSI, we are having exceptionally good professors in IIT Madras. Exceptionally good world-renowned professors. Okay, you can search and see. They're world-renowned. So therefore, in GATE 2019 question paper, you will see very good VLSI questions only. There were a lot of MOSFET questions, right? So okay, these are past transistors again. Okay, so how do you identify like this? So if one side there is a voltage, it is getting biased. MOSFET, what will a MOSFET do? It will pass the logic. Okay, so what normally happens is, so if the 3 volts I am getting here, okay, I am getting a 3 volts here, the VT is 0.6 volt. Okay, so the voltage here will be 2.4. VD is VG minus VT. This we have seen. So in a past transistor, this is what happens. Okay, so your V threshold voltage is 0.6 volt, that is given, and they have asked you to find V out 1 and V out 2. Okay, so now 3 volt is coming in, 3 volt at gate, so this will be 0.6 volt drop, and the 2.4 volts come at output. Okay, so now this is again 2.4 volts. All these are NMOS transistor. Okay, so this again will be on. So this is again passing, trying to pass. So this will be trying to act as a short circuit. But now we are not having an ideal thing. They have given a threshold voltage and all. So again this is 0.6, and 2.4 minus 0.6 will be 1.8. So V out 1 will be 1.8 volts. Okay. So 2.4 volts is the voltage here at this point, right? This is the same 2.4 volts. And the drop is 0.6 of VT, okay, which is coming between your gate and drain. Okay, it is basically the VGD. Okay, so now that is 1.8, and with the same logic, in the second circuit, what will happen? This is 0.6 drop, this also is 0.6 drop, this also is 0.6 drop. Okay, so this will have a 0.6 drop, this will come to 2.4. Okay, biasing is fine. This will again come to 2.4. Biasing is fine, and this will again come to 2.4 volts, and therefore your option is C, 1.8 and 2.4. Okay, just have a look at it first. Let me know if you have any doubts. Okay, so this was also simple enough, I think. This question was also a very simple kind of a question. So this is fine with everyone. I think when we were doing the MOSFETs, we had discussed the concepts in a way that this should be clear. Okay, so now coming to the next question. Source and drain is always decided with respect to which is having the higher voltage. Okay, in NMOS and PMOS. And in any case, source and drain is always decided with respect to which voltage was higher. Okay, and in pass transistor, actually it is just the passing of the voltage, like input to output, is what I think matters most. Okay, I don't think you need to decide it in that way. Because there is no biasing concept and all. It is just acting as a switch. So you are giving a gate voltage, the switch is on, it will pass the voltage. That's it. So there will be a drop of threshold value. That's the only concept. That whatever is passing, there will be a drop of 0.6 volts. Okay. So now for CMOS, this was a question from CMOS inverter. Okay, but even if you have not studied the topic, this could be solved. Because if you see the CMOS inverter, it's like this, right? Okay, so again it is not taking in. So in the question, basically they have asked you the ratio of the aspect ratio values. Okay, so CMOS inverter, you know the design, right? So in CMOS inverter at this point, okay, at this point, you consider that your current through the circuit, that is a same current flowing, that is IDP, which is flowing, the drain current because of the PMOS is equals to the drain current because of the NMOS. This is an instantaneous current, and actuality there is no current in CMOS inverter because one of the MOSFETs is always off. But when there is this dynamic transition happening, okay, there is a dynamic current flowing, which gives to your dynamic power dissipation also in CMOS inverter. Okay, so that is a different detail. But anyways, considering that IDP is equals to IDN, the drain current is equal, and you have all the values that is required for finding out the drain current. Okay, so what is the drain current formula? We have seen the drain current formula: half mu n cox W by L VGS minus VT whole square, right? So now for IDP, it will be half mu P cox W by L P, right? And what is VGS? So in your PMOS, your this voltage VSGP, and remember the input is given as VDD by 2, right? So I'm writing directly VDD by 2. So what is your VSG value? It is VDD minus VDD by 2, right? VDD minus VDD by 2. So therefore VSG I can directly write as VDD minus VDD. So let me just, since I have written a common formula, let me just write it in mod values, right? I like this I'm writing. Okay. So for IDP, it will be VDD minus VDD by 2 minus VTP square. Okay. And for IDN, it is half mu n cox W by L n. What is the value of VSG? So this is the VGS, right? So what is VGS? It is VDD by 2 for NMOS, right? For PMOS also it is VDD by 2, but how? VDD, the supply minus the input is what gives you VSG. But here directly VDD by 2 minus 0 volts is what will give you VGS, right? So simple KVL. So this is VDD by 2 minus 0 minus VTN square. Okay. So you have all the values. Okay. Now plug in the values and solve this and let me know the answer. Okay. So I have minimized the screen, but yeah, it has come. So please look into the values, plug in the values, and then use this condition which I have written, IDP equals to IDN, right? And then from there you will get the ratio W by Ln and W by P ratio, which is asked in the question. I hope it is visible. Okay. You understood what has to be done, right? I will ask you guys what answers you are getting. So start solving. I'm waiting. Okay. Any doubts in the question you can ask. Or did anyone finish solving? Okay. Okay, Hari Prasad has got 0.225. Let me know others what values you are getting. Anybody else solved? It was a simple solution. So 0.225 is the answer. Okay. Now let me know if others are done also, because I will wait for this. Chandrasekhar, are you done?
Yes, ma'am.
Okay. Navneet, what about you? Are you able to understand what we are doing? Okay. So now coming to the next question. Okay. So now try to remember when we have done the amplifiers part. Okay. Because this question is related to that. So in the circuit shown, the threshold voltages of the PMOS and NMOS are both equal to 1 volt. They have given the threshold voltage. Okay. So let me just write it down. VTN is equals to mod VTP equals to 1 volt. Okay. And now all the transistors have the same output resistance RDS. Okay. RDS. Okay. So that means they have told us that RD is present in the circuit. Okay. So RD is present in the circuit. And RDS is 6 mega ohms. Okay. Now other values they have given, other parameters they have given, right? Okay. Now ignoring the effect of channel length modulation and body bias, that means lambda you did not take, right? The gain of the circuit is. So the first thing is that I have to find the gain of the circuit. Now for you, finding out the gain, if you start making the small signal model for this, you will lag behind. You have to look into this circuit and understand what can be the gain of this circuit. Okay, so for that what you will do, so first see the right side of left side of the circuit. Okay, that means this part. Is this part in any way contributing to the gain of the circuit? So even if it looks like it, it is not a differential amplifier if you are thinking like that. Okay, what is this circuit doing? So you see, this kind of circuits are there to bias your transistors. Okay, yeah. So these kind of circuits are there to bias your transistor. So the main transistor that you are having in this question is the right sided circuit, this one. Why? Because V in is going input to the NMOS and V out is coming out. So if I want to find the gain will be coming from here. Okay, so you know from the property of the MOSFET, any voltage, if the voltage is inside this, so let me name this, this is M1, this is M2. Okay, so if the Vin is input to M1, then there starts a current flowing which is GM1 Vin. And since there is no other transistor connected to the source, there is no other transistor here, right? It is directly ground. Therefore, it will be GM only. We have done this, if you remember, we have done this exercise that if there are multiple transistors connected in cascade like this, the GM changes, right? But if it is connected in this manner, that it is directly grounded, the MOSFET is grounded, then the GM is as it is. Okay. So GM1 Vn is the current that flows. Okay, and that means whatever output is connected to V out, that will, so basically there is a current which flows on like this, GM1 Vn, right? And whatever across it resistance it is connected to, that will give you V out. Okay, so okay, I have again drawn and it is not coming, so I will wait for some time for it to show. Okay, so the left sided circuit is only there to bias these transistors. It is simply biasing your PMOS. Okay, because the PMOS needs bias. The NMOS bias will come from Vin. From there you have to give it a DC bias. But PMOS, it is getting the bias from that side. Okay, so now you see, now the diagram is showing up. It is just like there is a current source GM1 Vin, and across it whatever RL will be there, that will give you V out. So now the question is, what is RL? So what is RL? For RL, what you have to see? You have to see it from V out perspective. You have to see from this side, right? Okay, so you have to, okay, so again the arrow is not coming. I have drawn it. So let me wait for some time. Okay, so I think I can just share the screen from the question paper and directly tell you how it is working, because I'm not getting the internet in my iPad. So okay, so this is the question. You can see it, right? Please respond. Okay, I think you can see it. Okay, so you see now that this part I was talking about. So because of the V in, there will be a current here which is flowing. Okay, so wait, there is a better way of doing it, I think. Let me try that. New. Okay. Okay. So now you see that this part here, right? This is nothing but like a current source. Okay. GM1 VN. Only this GM. Because we have, so if there would be some transistor MOSFET present here, then the GM will change, right? And that we have seen. So this is like a GM and whatever is an RL. So what will be the RL? The RL will be whatever I can see from here. So R up, okay, and here R down. And we have seen what is R up and R down. We have seen that R up is PMOS, drain to source resistance, so RDS. And R down here is also RDS because NMOS is present and RDS value is given, right? So what will be your gain? AV, okay, that is GM1 equal into GM1 into RDSP, that is the up resistance, parallel with RDS N. Okay. Okay, so this is your voltage N. So now the GM1 is what you have to find out because RDS is given. So GM1 you have to find out. Now you know from formula that GM is nothing but under root 2 ID mu COX by 2 W by L. This is what your GM is. Now you have to find ID for this, right? Because ID is not given. The rest of the values are given. So this is what is the GM1, that is for the NMOS. That is GMN. Right? This is nothing but GMN. So now this is NMOS, right? This is GMN, this is W by LN, mu N, okay? But you see the ID is equal for both, right? IDN is equals to IDP. So why I am saying this? Because if I want to find ID for NMOS, I need to know the VGS, which is an unknown value here, right? I am unable to see VGS. But you see from here, you see the VSG can be found out, right? This can be found out. Okay, so this can be found out. So what is VSG? Since all the transistors are having equal thing, VSG mod value is nothing but 2 volts. Okay, VSG is 2 volts. Now plug in this value in the formula of ID that we have written earlier also. What it is half mu COX W by L VSG minus VT whole square. Plug in this value and you will find the value of ID from here. Okay, you will find the value of ID. Okay, so quickly calculate. I am also calculating. It is half of 60. W by L is 5. Then 2 minus 1. Okay, so this is 150. 150 microampere. Okay, so what is GM now? Under root of 2 into 150 into 5 by 2 into 60, right? I have written it opposite. So W by L is 5. Okay, so that is what I have written. So quickly say what is the value you see. 2 into 150 into 2.5 into 60 gives you 1 GM. Okay, and then you have into 3 megaohms. Okay, I think I have done some mistake in the calculation of ID. Just cross check it once. One second. Yeah, ID value is correct. ID value is correct. Okay. Oh, okay. I have understood what I have done now. Okay. So the 2 here will not be there. Yeah. So now you see what you are getting. So under root of 2 into 300 into 60. And then you find AV from here. Okay. So whatever you get, the answer is there. Okay, so I don't have the answer now, but this is the process. And if you, so for this you need not, the main catch is that for this you need not draw the small signal model. Okay, so basically this circuit and this circuit here, if you see, if I make this kind of a circuit, V in input, here V out, VDD. If I had made this kind of a circuit, it would be easier for you, right? And if I bias it with some voltage, so this will be having the same gain as what is here, GM1 RDS parallel RDS, right? And these two PMOS here are doing the exact job of biasing. So from this 4 volts, these two PMOSs are biasing this node so that the proper gain can come from here. Okay, so this was the main catch. Okay, so solve the circuit and see whatever answers you are getting. So I'll go to the next question then. Let me check what the next question I had taken. Okay, yeah. So this is a much simpler question than the other. Okay. Yeah, it's shared, right? Okay. So in this circuit, V1 and V2 values are given. So V1 is 0 and V2 is VDD. The other relevant parameters are mentioned in the figure. Ignoring the effect of channel length modulation and body effect, the value of I out is. So this is a question of the current mirroring concept. So what is the current mirroring concept? If so if there is a current I flowing here, okay, and this is W by L once, let's say W by L 1, and this is W by L 2. Okay, so what will happen is the I at I2 will be W by L 2 upon W by L 1 into I. Okay, and I2 is the current flowing from here. Okay, so this is what the current mirror does, right? So now here W by L is given as 2 here. Okay, so let me just write it with some other color. So W by L is 2 here and it is 3 here. So that means I2 will be what? I2 will be 3 by 2 of I. Now I is 1 milliampere, so it is 1.5. Now the question is, what will be the current in the upper two branches? So this one is 1.5, right? This is 1.5. So here comes this part of the question. V1 equals to 0 and V2 equals to VDD, right? So if V1 is 0, that means this is off. This is off. That means there is no current from this side. Now V2 is VDD, that means this is on. So the entire current flows from here. So this is 1.5. The entire 1.5 flows from here. Okay. So now again, if 1.5 is flowing from here, then this is 10. This is given as 10. Okay. This is 10. W by L is 10. And this W by L is 40. So what will be the current I out? That is what they have asked. So I out is 40 upon 10 into 1.5. Answer is 6 milliamperes. Okay. The catch in the question is V1 and V2. Now this is a differential amplifier, right? This is kind of a differential amplifier, right? So if V1 is, suppose both are given as VDD, if both are on, then there would be then you have to see, okay, what is the aspect ratio here? Okay, both aspect ratios are equal, so I can consider that equal currents are flowing from both the sides. So in that case I can consider, okay, 0.75 from here, 0.75 from here. If all other biasings are equal and single and differential, if the biasings are differential, then we can take same currents to be flowing from here, and in that case it will be 0.75 into 4. Okay, the answer would have been 3 milliamperes. But in this case, however, that they have given the biasing in this way, V1 is 0, V2 is VDD, your answer is 6 milliamperes. Okay, so this is the catch in this question. So when you do this question, analyze that part. Okay.
Ma'am, answer again, ma'am.
So basically, the current mirroring part you understood, right? That this is the current which if, okay, let me just erase all ink. Okay. So now current mirroring concept is that if there is a current source, I directly use a current source and there is a MOSFET here, and it is connected, the base is connected here, so that the VGS is equal. You see the VGS of both the MOSFETs are equal. Then what happens is the current in this branch, the drain current in this branch is the W by L of this upon this into the main current. So here it is 3 by 2 into 1. So 1.5. Now 1.5 milliampere is flowing from this branch. The same concept I can apply here also in this branch, right? Mirroring concept. So what will happen? If this is 40, this is 10. So therefore whatever current flows in here, that current I, so I out will be I into 40 by 10, right? Till here it is fine. So now I have to find I, right? So now what will I do to find I? This is 1.5 I know. So how is this 1.5 coming from this 2? Is it getting equally distributed, or it is getting halfway, or like 1 by 3rd, 2 by 3rd distributed? How will it be decided? It will be decided by this biasing, V1 and V2. Okay, it will be decided by this biasing. So now what will happen is that since V1 is 0, this is 0, so that means this NMOS will be off. Okay, most of the current will pass from here because V2 is VDD. So therefore all the 1.5 is passing from here. That is what we are going to assume. And therefore it will be 1.5 into 4, 6 milliampere. Now suppose if V1 and V2 biasing were given in a way that they are equal and differential, like that kind of biasing, if it is there, right, equal biasing is there, then in that case it will be, the current will be half distributed, because all other aspect ratios are same. You can see it will depend on the transistor also. So this kind of an arrangement, it is like a mirror image, right? So this arrangement is important. So it is like a mirror image from here, right? So basically equal current can also flow if V1 equals to V2 is given. So that is what happens is differential amplifiers, right? But in this case, V1 is not equal to V2. They have given V1 0, V2 is VDD, and therefore all the current flows from here. Is it okay? Any questions? Okay then. So I think then I will stop here. Sorry for the this disturbance in the class, because I did not have my router here, and the internet is actually very pathetic in IIT Kharagpur. So yeah. So anyways, I think if you guys have any problems, try to solve other questions as well from GATE 2019. Okay, related to this analog domain, and if there is any problem, please ask me. I'll try to compile op-amp questions and do it in next class. Okay. Okay then. So if there are no further doubts, then I will close the session here. Okay.